Good evening, good afternoon, wherever you are in the world. I see that we've got a number of people from around, and that's great to have. So we at the end of this, we'll have a Q&A, and we will also give you some links to some handouts that you can then view. Right, so let's get moving into it. This will be recorded, and you'll be able to monitor it later on. All right, so we're talking about powering the shift to electric vehicles and fuel cell vehicles. And we're looking at both electric and hydrogen costing. And we're specifically looking at the cost differential between electric and hydrogen. There have been some excellent questions which we'll address later on, talking about the distribution costs. So here's our agenda for today. I'll give you a little bit of an introduction about myself, electric vehicles, hydrogen, and just share with you some of the overlap there. I'll show you some outputs from a tool called Battery Optimization and Lifecycle Tool, which is something that WSP has developed and we use to examine the electrification or hydrogen process. We'll look a little bit about battery technology, and I'm focused specifically on heavy vehicles. You can see on the right-hand side there, Amazon's 37 tons heavy good vehicles, which are going into UK at the moment. And then the bottom two pictures are from SEA in Australia, and they're doing a different type of development, but along parallel lines. And I'll also share with you some retrofits that are being used. We'll look at hydrogen costing and the sensitivity that that has, and then we'll go into the Q&A. And as I've said, there are a couple of handouts that you might find interesting. So who am I? So I'm a technical director for WSP in New Zealand, but I come out of Africa, and I've had over 30 years experience in everything from hard rock mining, 1.5 kilometers underground, where we were electrifying, and that's where a lot of the electrification experience that I have comes from. I work mostly in the high voltage side of things, and I have the dubious honor of managing to destroy a number of switchgear systems during testing at TCA. And as one of those, we managed to launch one of the ventilation units about 600 meters across the road into a neighbor's property. Not something you want to do every day. But I find unless you try something, you never push the envelope. You never find anything new. And we've done the same with the buses. So I'm chartered in the UK, in spite of my dubious history. I've worked in Africa, Europe, USA, and Australia. And at the moment, I'm working a lot in transport, marine, the power utilities, and of course, with the councils that are grappling with this whole issue of decarbonisation, electrification. I'm working on zero emission in both Australia and New Zealand, as well as USA and Canada. The picture that you'd seen up above was a prototype that we're working on in conjunction with Auckland Transport, which was hydrogen. And the reason behind that is driven by these numbers. And basically, and I'm using pre-COVID numbers, in 2018, New Zealand was 84% as an average renewable generation, but we still imported 364 petajoules of fossil fuel. Of that, transport used 235 petajoules. So you can see the figures there overall and how much was renewable. In spite of New Zealand's admirable record, we still imported a lot of fossil fuels. So if we could reduce the amount of fossil fuels being imported, we would improve our balance of payment, we would improve our carbon balance, and because it's renewable, we're generating it ourselves. So if we were to do that and just aim at transport, we would need to replace about 313 petajoules. Now, let's put that in an electrical context. Typically, a 5 megawatt turbine runs at about a 41% capacity factor because the wind doesn't blow all the time, and that gives you about 0.065 petajoules. Then you also need to allow for downtime, maintenance, etc. So If New Zealand was to replace 80% of its imported fossil fuels with renewable generation, we would need something like 20 wind farms or geothermal operations or solar farms, or, as I would like to see, some new marine generation, 20 of those, each of 250 megawatts to produce that 313 petajoules. Now, here's the kicker. If you want to use hydrogen in that process, you must add in the efficiency loss. And that equates to another 6 wind farms of 250 megawatts. So now the question is not can we do it, but should we do it? What do these costs show? And where is the risk and the variation there? Now, again, let me just be clear. As soon as you add any storage to a system, there are losses. Right, let's get moving into it. So now I mentioned to you battery optimization and life cycle testing. So how and where do we get these figures from? So this system is actually very sophisticated and we use it for all forms of transport. So we look at the physical characteristics, the powertrain. This particular one was set up for a bus, but that could be a bus, a vehicle. You can see the Isle of Wight hybrid energy ferry down on the right-hand side. As long as you've got the characteristics of that vehicle, you can put that in. You can see the power consumption, and for a vessel, you might be saying, are we going with or against the tide? What's our laden weights? And what's the environment that it's operating in? Then within the actual vehicle itself, you need to have a look at what is the efficiency, both in terms of how do we charge it, or are we converting hydrogen to electricity? What's its output power? What's its efficiency? What do these charge curves look like? What are the connections? Do those connections have an efficiency loss? Then you look at what that vehicle's doing. And that's your revenue round trip services down here. And that's everything from, this is the terminus where the ferry comes in, or this is where the bus comes in. These are the elevation changes that it has to have. Now, with a marine vessel, your elevations will only be the tide that it's working against. But for something like a heavy vehicle, where you're going up and down hills, that can be quite substantial, and you can both gain and lose through that. We then look at things like route alignments, the number of layers, the frequency of the trips. And remember, whoever's the fleet owner, they're going to have certain revenue aspects of those trips and certain non-revenue aspects. So we include that as well. So if the bus driver takes the bus and he goes off to go and fetch lunch, well, that's a cost to the fleet owner. And then, of course, the other part of it is ridership and cargo loading. Obviously, the more weight you put into the vehicle, the more you have to consider that in terms of starting and stopping. And obviously with a vessel, the deeper you're running it into the water, the greater the resistance. Right, on the top right-hand side here is an electrified vehicle. You can see here in New Zealand, we typically run 2 axles on the smaller vehicles, but some of the larger vehicles, especially because of the weights, when you're 500 plus kilowatt hour batteries, we're shifting over to 3 axles. Now, I'm going to come back to the slide later on, so don't worry if you don't get all the information now. So what you've got here is petrol, diesel, then hydrogen, and then direct electrification in comparison. The grid, well, that's a common factor right the way through, okay? And it doesn't matter whether you're using that grid to feed a refinery, or you're using the grid to feed a hydrolyzer, or you're using the grid to charge battery. I've taken that as the 0 point. Then you can see the different processes, electrolysis, maybe you've got some CO2 air capture, that side of things. You've got transport and storage costs, and that gives you your fuel. Remember, hydrogen is an energy carrier. It's not a pure fuel. Then you move down into how do we charge it? What's your battery efficiency? Is there a conversion to electricity? Is there now an inverter? And how much do you actually get rubber on the road? The black figure here is pretty much where we are now, and the figure in gold here is about where we think we'll be in 2050. So keep that in mind as we go forward. Now, on all of the slides, we've tried to give you references as to where they come from. So now let's kick into the costings. So Lazard is a common standard that's used in multiple countries. It is available on the internet. You can search. I've given you the link in the bottom right-hand corner there. And we're looking at the levelized cost of generation. I've brought everything to US dollars, and this is unsubsidized. Again, keep that in mind. Often with new technologies, we've got subsidies going along, but with the fossil fuel industry, we still have subsidies in place. So a couple of questions have come through asking for costing, and sometimes the most difficult thing is to unpack the subsidies that are buried in the system, tariffs that are beneficial to one but block the other. All right, so now Lazard presented this graph, which is actually quite interesting, and it's a good place to start. It looks at renewable energy generation and how cost competitive they are with conventional generation today. But they also give you a couple of scenarios, and the scenarios create those bands. So if you think about a wind farm, you may have different geographic location. Obviously, if you're going to ship a wind turbine down here to New Zealand, your logistics costs are very different to shipping a wind turbine to Singapore or Hong Kong. Now, the little figure in gold down here is what happens if you start taking that offshore. So what you've got to remember is that it's not just the geographic location, but it's the entire environment that you're operating in. So typically, we're seeing 28 to 54 US dollars. That's per megawatt hour. So it's a fairly substantial amount, but if you go offshore, add roughly another 35. So again, you can see these figures show you the changes as we're going forward. Now, what you're also seeing is that there is a decline in price, because remember, when we're talking about hydrogen, it's all about tomorrow. It's not openly available today. You can't walk in as you can with a wind turbine and say, I want 5 megawatts now, when can you deliver? It's a developing process. And the target is about US dollars $2 US per kilogram to be similar to diesel. That's where you need to be at the pump to get some form of break even with diesel competitive. So part of what we're seeing is, yes, hydrogen costs are declining. So here's least costs of energy for generation for wind over the last few years and for solar. And you can see they're beginning to plateau. And in some cases, 2021-22, with the impact of COVID, logistics, cost rising, London's metal exchange, we've actually begun to see a bit of a kick up here. So that probably means, in terms of the current technology, they're leveling off, and we're now looking for the next technological breakthrough. So now let's get into hydrogen. First thing to remember is read the fine print. Assumptions are dangerous, and even though they are laid out, sometimes the consequence of those assumptions is not clearly understood. So let's first of all look at it. So this is a PEM electrolyzer. So this is the highest efficiency. This is a membrane type electrolyzer, although there are some technologies which indicate we might be able to get away without a membrane, which would bring the cost down further and hopefully the efficiency up higher. But what you must remember is that the least cost of hydrogen is calculated as delivered, and this is in per 100 megawatt units. So this is not small units. Here in New Zealand, we're only working at 1.5 megawatt units, and we'll have multiple modules. This is multiple modules at 100 megawatts plus. But these costs are based on a 15-year horizon, 2035, with no additional conversion, storage, or transportation costs. So when we go back to that graph I showed you earlier on, you need to understand that and see where that puts you on that graph. Now, what you need to also see here on the right-hand side is your capital cost is very sensitive, and you can very quickly get out of that $2 figure. So here's your energy cost in terms of dollars per kilogram, right? Sorry, your energy cost in terms of dollars per megawatt hour against your capital cost, and you can see your smaller sitting in here in your box, that's your target. It's a pretty tight target. So if your capex rises, you go out of it. If your energy cost rises, you go out of it. Down the bottom here is the next kicker, is that the utilization to hit these figures needs to be in this area here, 80 to 90% utilization. So if somebody says to you, no, we can use hydrogen and we will only use off-peak and we will only run 8 p.m. to 5 a.m., utilization then becomes a problem because the rest of the day that asset is standing unused because the energy cost is too high. So read the assumptions carefully and understand the consequences of this. And it's very easy to get pushed down this way. Once you start getting pushed down that way, bear in mind this is 2035, you may have a problem. Okay, so now a couple of questions, and to be honest, I don't have the answer. My crystal ball's broken, the pixie dust has run out, but the question is, are we going to reduce capital costs by 60 to 70% in the next 10 years? As I showed you with some of the slides, yes, for some technologies have seen that. But the question you need to ask is, what are the assumptions behind reaching that? And what you need to also remember is that to reach this, there is substantial infrastructure that needs to go in behind this even before you get to this stage. So watch out for the assumptions. So now, irrespective of whether you're running hydrogen or battery, you have an impact on the grid. And that's why I was showing you how much electrification in terms of generation would need to be added to New Zealand's grid. So if we had, for instance, a heavy vehicle depot and we're charging 500 kilowatt hour batteries, and we have 57 of those charges, we end up with a peak. And because we're limited and we're only going to run after hours from 8 p.m. at night as these trucks start coming in, we start charging them. Based on an 80 kilowatt hour battery, sorry, 80 kilowatt charger running at 85% efficiency, you can see we get a couple of peaks, about 3.1 megawatts. But the problem we have is at 6 a.m. in the morning, we still haven't finished charging. So the easy solution is to increase the size of the chargers. Let's go to 150 kilowatts. The efficiency is still the same. Usually we can get a little bit better efficiency. We only need 45 chargers because those buses that came in round about 8 o'clock can be charged pretty rapidly, and we end up with a dip until the next fleet of trucks come in. Now, you can do some good things. You can do some maximum demand control and say, we don't have to charge every heavy vehicle as it comes in. We can level that down and we can start shifting things over. And because the chargers operate faster, bear in mind the amount of energy is the same, but the amount of power increases because you're doing it in a shorter time. By 4 a.m. in the morning, we're charged. Now that gives you some opportunity in case there's a power failure. Now, this is generated by our package called Bolt, and in real life conditions, here in Auckland, testing Bolt against heavy vehicles, buses running in the market, we've found that we're more than 96% accurate, to the point where we can actually show you which driver is driving. Okay, so what happens now if you charge during the day? You get another peak. Can you retrofit heavy vehicles? Yes. This is one here from Janus Electric, and this is a T403 Kenworth. And you can see the size of that battery. So this is 500 kilowatt hour plus, loaded with a forklift. It's done as a retrofit, so you can sweat the assets. So now let's come back to this graph, and this is where things begin to get interesting. First of all, efficiency is important, but it's not the only metric. Effectiveness is just as important. The second thing to remember is those assumptions from Lazard excluded transport, storage, and distribution. So those figures from Lazard, where we were already just on $2 per kilogram for hydrogen, by 2035, we were sitting here. Still got a loss or a cost for transport, storage, and distribution. Hydrogen doesn't need a charger. It's not too worried about the battery efficiency because you just use the battery to start the fuel cell and you use the battery for your regenerative braking. And then we come down here, and this is the kicker, 54% hydrogen to electricity conversion. That's where a fuel cell is at the moment. Possibly we'll get to 60%. Now, the other thing you need to realize is that every hydrogen vehicle is an electric vehicle, but with a smaller battery, a fuel cell added, and a hydrogen tank. So this here is still the big issue. So that's where we need to get an improvement. And the problem here is around this here, storage. As soon as you add storage, you add cost. So the question is that cost worth it? Right, so we're almost at the end. We're about to start Q&A. So if you've got some questions, you can feed them in to our host, who can then feed them through to me. So in summary, electric trucks are on the market now. Here in New Zealand, we're already running refuse trucks in trial. We've got a lot of heavy buses that are already electric and are in operation and are doing ranges of 300, 350 kilometers without a problem. We also have some trucks with 500 kilowatt hour batteries, which are doing ranges in excess of 400. Some of you may have seen the recent announcements on solid state batteries. There are also structural batteries, which now replace a structural part of the vehicle with the battery. So that brings the overall weight of that truck down. Those electric buses are in widespread use. We already have an electric ferry, which is already in commercial operation. We have 2 more electric ferries, which are already on order and are being constructed, and another 18, 19 to follow. And that's just for Auckland. Around the world, we're seeing in a number of different places, and in the white paper, you'll see a couple of examples that we've been involved in, including Ellen over in Denmark, which draws a substantial amount of power, well into the megawatts when it docks. The other thing to remember, adding any form of storage reduces your efficiency because there is a round trip efficiency loss. Power in, storage, decay, power out. Now with hydrogen, it's a lot smaller, but the question is, what do you gain for that loss and the cost? And if you require a range much greater than 400 kilometers, possibly that's the answer for you. The other thing is that hydrogen needs substantial upstream investment to meet those 2035 expectations. Here in New Zealand, we're in the trial stage. So yes, we have hydrogen bus under trial. I have one in the fleet that I'm working with. And there are Hyzon trucks that are coming in. There are other fleet vehicles that have been tested, but they're currently leased because many of them are still in that stage where they are being tested. Okay, there's a couple of resources down there for you, and they will be available as part of the handouts. So I'll hand back to our host for the questions.
Thank you, Kristian, for your presentation. Yes, thank you. So you can log your questions in the question box like Kristian mentioned, and also the handouts are available, the slides are available as a PDF. So we received before the webinar some questions from the audience. Thank you for logging those. I will start with the first question from Stephen in Australia. Does the cost review cover the natural resource component and impacts to make the batteries or infrastructure associated with both?
Now, that's actually an excellent question because it frames what we've presented here. So I've just looked at the costing for hydrogen versus electric from the grid downwards, as I showed you on the graph. So when you look at the whole aspect, you have to consider, it doesn't matter whether you're talking nanomaterials in fuel cells or the lithium that's required in the current lithium-ion batteries that we're using. Those natural resource impacts do need to be costed. This presentation, I haven't done that. There are some sources out there of that information, but it's scattered, and to be honest, it's not in a consistent format. So again, remember that irrespective of whether you're looking at hydrogen or electric, both of them have to have at their core an electric vehicle. You're adding the hydrogen on top of that, right? The other thing that you need to have a look at is when you're talking about life cycle costing, we need to do the same for internal combustion engines. So irrespective of your technology, you need to compare apples with apples. And then, as I mentioned previously, part of the problem is how do you remove subsidies that are embedded in that so that you have a clear comparison? Because sometimes the assumptions could be it's at the pump, and that already includes some form of subsidy because the tankers are paying a different road user charge, for instance. All right, so unfortunately, I don't have a full answer for that, but hopefully that's pointed to you some of the assumptions that underlie that need to be looked at.
Thank you.
To you, Sharon.
Another question from Bradley from Australia. Are there models that amortize cost of any hydrogen or electric distribution network, build costs over the life of the contract?
All right, now we do have separate models for the distribution networks. We have per unit costs. But the issue is that you've got to remember that each and every one of these is geographically specific. So as you've seen, I work across multiple countries, and one of the big assumptions that you cannot make is the cost per kilowatt hour of power in this country is the same as our neighbor. You cannot assume that the cost per kilometer of 11 or 110 kV overhead distribution is the same. It isn't. And part of that is because of the nature of the country, the geography, and even the standards that are used to construct that. The other aspect that we're finding as well is that many of the existing installations would have been done with overhead power reticulation, but the new installations, because of the change in standards, legislation, and even technology itself, are now HV, HDPE cables, sorry, HDPE ducts with PEX cables in the ground. All right, so your costs now become quite difficult to compare because the overhead power line is much cheaper than an underground cable. But you may need to put in underground cables because that's the standard. So I'm seeing a lot of variation around infrastructure. So I don't see a single model that's going to answer that. You probably need to build it for your country. So upstream costs also differ. So for some locations, they may have a first mover advantage because there is an existing surplus power there, because there's a large industrial factory adjacent which closed down and that power is available, or the network has some capacity that can be utilized. But as subsequent loads are added, that cost escalates. So again, that's very difficult to model without knowledge of the specific geographic location and its linkage. So in terms of that economic assessment, the framework that we use for that, for each geographic location, typically we'd follow ISO 55001 whole of life costing, and we'll try and look at that. And again, we'll have to make some assumptions. We would say from the zone substation, local distribution only to the point of the charger or the hydrolyzer, and try and fence it in that way around. But no, we don't have general network models.
Thank you. Another question from Matthew from Saudi Arabia. How is the whole life cost looking? Are there any ROIs examples yet?
Now, that's actually quite a good one. And I did actually prepare further slide. There we go. Right. So let's look at whole of life. So this, we're dealing with a number of fleet owners in a number of countries with a number of aspects. And to give you some publicly available information, I've referenced an American paper here, but this is what we're seeing in multiple countries, is that yes, the upfront costs of a new technology like this are higher. Your cash flow is negative in the case of electric, first 3 years, and then swings positive. Now, that data is consolidated across a large number of fleets. WSP's had fleets that we fed into this. A number of other consultants have been involved in feeding this information in. And even our own Bolt models and work with our own fleet owners here in New Zealand, even with our higher logistics costs, still show that 3-year break-even point is about right. Now, there are some assumptions on this. We assume the bus travels around 52,000 kilometers per year. If you're traveling much higher than that, you find that you get an earlier break even because of the impact on the lower maintenance costs. If you're traveling substantially less than this, you may find a different result. But remember, stop-start traffic, even though it doesn't have high mileage, does a lot of, or creates a lot of wear and tear on drive lines. We've assumed the average lifespan of a bus is about 12 years, and we find that common across many countries. Obviously, rust, the abuse that the vehicle can suffer are key factors in here. So again, is this valid for your country? Rough diesel bus, around 480,000. Raise a few eyebrows over that consumption figure, but that's what it consumes in an urban route. So a bus, electric bus, not quite double that. Remember, a hydrogen bus may be higher again because you're buying an electric bus with a lower component, but adding some additional aspects to it. Then you've got to add the cost of electricity. You've got to add the peak MD charges, as I showed you. You need to make some assumptions around the battery life. And we're seeing a lot of batteries now being guaranteed by the manufacturer 10 years. So that's what we've used. Many of them last longer than that. You can see the slide down here. Seeing lower maintenance costs, warranty coverage, that side of things, but definitely a higher upfront cost. Discounted break even, somewhere around that 3 to 3.4. So to go back to the question on return on investment, simple payback, 3.4 years, a discounted payback, 3.6 if you want to look at the cost of capital. That may vary depending on what your capital costs you in this area. But because the cost of maintenance is lower, we still find that the used bus comes out well ahead when we get to the 12 years. Right, so I hope that answers that question.
Fantastic, thank you. Unfortunately, we don't have time for additional questions. We have also live questions. Unfortunately, Kristian will be able to answer these directly by email. So we're at the end of our webinar session. Please feel free to follow up directly with Kristian via the contact details shown on the screen. And I would like to thank all attendees for joining today. Thank you very much for your time, and thank you, Kristian, for a fantastic presentation.
Thank you. And if you email me, I will contact you back. Thank you.
Thank you.